All right, I think this is about everybody that was going to be able to make it, so we can go ahead and get started here. If you guys didn't already hear this, the whole thing is going to be recorded. So there's, there's a camera back there, and then the audio. So this is going to be for everybody that wasn't able to make it today, in part because of rescheduling, and also in part because not everybody's even in Wisconsin who's invited to this. So if there are any questions, please remind me to repeat those questions, or potentially we'll be able to have a microphone moving around as well for questions so that they can make it into the recording. I do want plenty of questions because, this is sort of my topic area, and everybody here is from very different backgrounds with very different levels of understanding of what are markets, what's the electricity grid. So we're going to be talking about a lot of things. There might be a lot of different terminology that I'm just used to talking about when I give talks about the power grid, so please call me out on using too much jargon. And with that, we'll get started. Again, questions at any time. This is going to be about 2 to 2.5 hours, I think. We'll take a couple of breaks in the middle as well, because that's a long time without breaks to be paying attention. So who is this for? There's about 3 main groups here. The primary group that this is for is this future manufacturing project, which is taking a look at sort of electrifying chemicals industry. What are different ways that we can run electrolysis systems to create different useful chemicals? And it's this integration between electricity markets and chemical markets. So a big part of this talk is to give all these chemical engineering and chemistry people some context for how do electricity markets work. If this is something you're going to participate in, how would you actually trade in electricity markets to do some of the manufacturing process? The other 2 groups that are here, so there's energy analysis and policy, which is this PhD master's minor certificate that you can do. I was a part of this program. The front row here is a part of that. I think it's a really great certificate to get you some context again of like how does maybe some of the research that you're interested in doing actually relate to some of the things like regulation and policy and some economics around energy. So it's a really great group if anybody's looking for a PhD minor still. And the final one is our power systems group here. There's some people in the audience from that as well. And yeah, so this is everybody in the room. Again, broad range of backgrounds on who is actually here, so ask lots of questions if there's something I talk about that you don't specifically understand. Who am I and why am I qualified to talk about this? So I'm a PhD candidate in power grid optimization, my final semester here, so I'm getting ready to wrap up. All my research is around mixed integer programming for wildfire risk on the power grid. So I don't really do that much on the economic side, but all my research is still about this grid optimization kind of planning, and there's some related things there. But in particular, I was, this past summer, a market optimization engineer at NextEra Energy. They're a really big renewable developer company, essentially. So they have right now about 25 gigawatts of renewable generation that they manage, which is more than anybody else in the world. They also have another 150 gigawatts that are in queue to be constructed in the next 10 years. So they're developing a lot, they're building out a lot, and they're also touching a little bit into the chemical side. They've announced about $20 billion in green hydrogen development. They've already started construction on a North Dakota ammonia plant powered by 800 megawatts of wind. So they are also a little bit participant in this space, and I've heard some of the context at the company of like how do they think about planning out how they're going to develop new projects, how do you size a solar plant and a wind farm to power an electrolyzer most efficiently and capture as much energy from that as possible and minimize downtime, because big capital costs, you want to minimize downtime, all that infrastructure. So a lot of interesting stuff there. And once I leave here, this summer I'm headed to Los Alamos National Laboratory as the director's postdoctoral fellow. I'm going to be doing more stuff about energy volatility, renewables, dominated power grids, and some of the research around that, which is going to get more into the economic stuff. But this is also, economic stuff has also been something I've been just very interested in, and I'm happy to now talk a lot about that. So what are we talking about? 3 main sort of categories we're going to go through here. First is sort of more of the history of the power grid. Not a lot of technical information here, but just like why does a power grid exist? How was it built? How has regulation happened, and then deregulation, formation of markets? All of that is pretty good context because we've had power grids for 150 years. We've had power markets for 25 years. It's been a very short part of the lifespan of the power grid, and there's important context that kind of leads into the formation of markets there. The next bit is going to be more about what are electricity markets, what do they do, how do they operate, what does a market operator do, what are the different products that get cleared in that market, and how do people participate in that, both buyers and sellers of electricity, what is all the participation of that. And at the end, we're going to take a look at some data, so some of the regional temporal patterns in electricity markets, just to give sort of a scale of, how do the seasons affect energy usage, and then also renewable energy generation. And we'll take a look at some little modeling examples to give an idea of how you could start to participate, how you would develop a model of something that would want to participate in energy markets. So before we really get into that, is there anything that people want more specific information on, things that I should focus on over the next couple of hours? If there's nothing specific, I'll just get going, and then we'll see when you have questions. All right. We'll start with sort of the history of the power grid. So the first ever central power plant was the Pearl Street generating station in New York City. It was on the south end of Manhattan Island. It was in the middle of that little darker grid of squares, and that was the entire region it could power. It couldn't send power any farther away than a few blocks. So this was sort of the origin of these central power plants. Electricity usage existed before this, but it used a little generator inside your own house to power your very expensive light bulbs, which is the only purpose of these at the time. A central operating plant, this was the start of economies of scale. You build a centralized generator that can run more efficiently, and then it can power more people's buildings more cost effectively. We have some good history in Wisconsin too, so less than 30 days later, the same month, was the first ever central hydroelectric plant in Appleton, Wisconsin, in my hometown. So I have been to the now nice restaurant that's in that former building. It's a cool place. But this was, the very early on. Again, this only powered 4 buildings. It powered light bulbs in the paper factory, the owner of the paper factory's house, and the building that the generator was housed in. And there's one more building. There are 2 paper pulp buildings that were there. But all that these original generators did was they provided lights. Power grids started to expand. So this is the Edison Electric Aluminum Company 1893 map. I put some red dots on there. They're a little bit hard to see, I think, but those are the 4 different generators that sort of helped to power this area around central Manhattan Island, that little column there. There was competing companies. So there was this is a 1906 map of the United Electric Light and Power Company. So they also powered the subway system in New York City at this time, as well as some electrical service around Manhattan Island. But, competing infrastructure wasn't great at this time. A lot of these lines are telegraph lines, but also a good number of them are also power lines. All this competing infrastructure wasn't very economical. Everybody was trying to take market share by building out infrastructure and also going bankrupt at the same time. So this is part of what leads to the sort of the natural monopolies of power grid companies. That having all this competing infrastructure doesn't make sense. You should have one company in an area that provides all the electricity, so they only have the infrastructure costs of the power lines that they use, and there isn't redundant power lines. And this was all of the continuation of industry mergers and consolidation that really happened over the next 50 years. So example here is that Pacific Gas and Electric. So they acquired and merged with more than 24 companies. By 1914, had the largest single operating unit of interconnected plants. So they spread out across 30 counties over the course of 15 years by just consolidating a bunch of different electric companies that were in California at the time. There were other developments that allowed these larger interconnections to happen, like AC power was able to move electricity for other distances than DC power. Larger generators that become more efficient also were a big part of this, and interconnections that improve the utilization of those capital expenses of those big generators. What does that expansion actually look like? So this is on the left here, transmission lines in the United States in 1908, there really weren't that many. By 1933, we'd built out a lot of transmission lines to connect more areas of the country together. And then you get what are called these interconnections of these large regions that are all connected together, and they can easily move power around within them. So there's, maybe 10 or so interconnections in this picture here. This is in the mid-1940s. But all these interconnections were able to increase the amount of electricity that got used by 60% while only building 25% more generation. You get better utilization out of the infrastructure by having these bigger connected systems. This is jumping to 2017 here just to get a context of where are the interconnections today. There are 3 interconnections in the United States: the Western Interconnect, the Eastern Interconnect, and then in Texas it's called ERCOT, which is Electricity Reliability Council of Texas. There is a very specific reason why Texas is separate, and it's because of federal regulation. So in 1940, parts of that Texas grid did expand outside of Texas. But in I forget exactly what year, it was the late 1930s actually, so that figure must be older. There was a law passed and included federal regulation of electricity utilities, and it was based on interstate commerce. So Texas cut off all the power grid that is outside of Texas, and now the federal government doesn't have any authority to regulate them because they don't participate in interstate commerce. So for federal regulation reasons, Texas left the rest of the interconnect, and now they have a lot of energy stability problems as a result of not being able to share electricity with the broader regions. Within these interconnections are these entities called balancing authorities, and they are responsible for balancing generation and electricity demand in real time. So within a region, there are these balancing authorities. They, within their own regions, balance this, but they can also trade electricity with their neighbors if they're in the same interconnection. So this is, we'll get to more of who these people are in there, but a lot of those circled dots are actually the electricity markets that we have in the US. So they're able to move electricity around within their own interconnections, but not all of the US is part of these markets, and we'll get to some of those details. So back to a little bit more of the history part of this, utilities as monopolies. So without these competing power lines, they are monopoly companies. There's a lot of regulation that gets introduced because of this. So the state regulation on rates of return, for example, for all the money that they invest into their infrastructure, they're allowed to recoup 7% of that as additional profits on top of the infrastructure costs. That's what they're allowed to charge ratepayers for their electricity to cover those costs. But utility commissions sort of govern that. They take a look at investment plans, so like this doesn't need to be here, it's too expensive, cut that down a little bit, and they're in charge more or less of ensuring that this is a public good, it's wise investment so people are not overcharged for electricity. So by 1915, as a part of this process, 41 states had utility commissions that are all responsible for regulating the profits of utilities. Some of these include like the Rural Electrification Act. So a profit-seeking monopoly utility doesn't really want to build power lines to rural areas because those power lines cost more than they're ever going to make back from the customers in rural areas because the land is so low density, there aren't enough customers along the miles and miles of power lines that they have to build. 1936 Rural Electrification Act kind of like forced these companies to actually build out and electrify rural regions of the United States. This Public Utility Holding Company Act, 1935, SEC had more regulations on utility holding companies. This also created the Federal Energy Regulatory Commission, as it's called today, which regulates this interstate commerce of electricity, and is very important today in terms of how electricity markets are allowed to operate. So as a utility, a single company owns all the generation, the transmission, and the distribution of electricity. You can think, so generation I think is pretty clear, is where you generate electricity. Transmission you can think about as sort of the highways of the power grid. You can move a lot of energy long distances, and then distribution is like local roads. It's the power lines within your neighborhood that actually move power from a substation to everybody's individual house. A single company owns all 3 of these steps in a fully integrated monopoly. There's no competition, everything is more or less regulated by utility commissions on what they are charged for electricity. The deregulation process started around 1978. This was PURPA, the Public Utility Regulatory Policies Act that was passed. This was largely an energy efficiency goal here. The idea was that non-utilities were allowed to build generators, and utilities are required to buy that electricity if it's cheaper than the utility building their own generator. The energy efficiency side comes from this, is that this is mostly for like cogeneration facilities. So there's a factory that needs some process heat to do some manufacturing. Instead of just burning coal to get steam for process heat, they can actually burn coal to power a steam generator and take the steam at the other end of that for their factory. So it's this energy efficiency goal in the 1970s that we had. And by being this manufacturing company, whatever, they had to do this anyways, it's actually pretty cheap for them to also generate electricity, so it's usually cheaper than a utility building their own standalone generator. So there are requirements called qualifying facilities on exactly how this would work. Further on in 1992, there was a bigger category of generators, most unrestricted, I would say, on who can build a generator and sell that power to the utilities. FERC Order 888 in 1996, though, is like the real start of the process of the formation of energy markets. It required non-discriminatory access to transmission lines. The idea here is you build a generator here in Wisconsin and you want to sell it to a utility in Indiana. You have to go through transmission lines in Illinois. That the owner of those transmission lines cannot discriminate against you because you're not selling power to them. They don't like that. They're selling power to their neighbor and you're using their power lines and they'll charge you exorbitant fees so that you don't do that. This restricted that. You have to give non-discriminatory access. You have to charge standard rates for access to the transmission lines. And it suggested that maybe the best way forward for this is actually to form a separate entity that operates the transmission lines sort of independent of the utilities and generator owners. And that's the start of the independent system operators, which today are who are the market operators in these different regions. They are sort of this nonprofit entity. They operate the transmission lines, but they do not own any infrastructure. Other people still own the transmission lines, but they decide how much power is generated in what places to most efficiently use all the infrastructure. And this is all pretty recent, like I said, in the last 25 or so years. And I have the years of market operations starting in these different areas as a list up there. A lot of these were entities that sort of existed prior to this, but this is a start of the market operations for these different places. So PJM, which is Pennsylvania, New Jersey, Maryland Interconnection, which is expanded a little bit now, started the first one in 1997. The most recent one is the Southwest Power Pool, which started as a power pool, which is a sort of separate topic, in 2007, and moved to full market operations in 2014. So all of this is really recent stuff. Question?
So where does funding for employees in ISO come from?
I have asked that question, and I honestly don't know. I think it might just be fees from the people within the utilities and generators in the region or something like that. Not totally clear to me how they make their money as this nonprofit. Oh yeah, the question was, how do the ISOs get money to pay their employees and stuff? And yeah, I don't know.
So why are there some regions without turning into the market?
Good question. The answer is not everybody wanted to form a market. Yeah, the question is why are there some empty regions in the US? So about 2/3 of electricity generation is within these energy markets, but they're not everywhere. Especially in the Western Interconnect, the only energy market is in California. So most of the Western Interconnect does not have a market, and the Southeast is sort of the rest of it. So if you want to participate in electricity markets, you cannot do that in these large regions of the United States. It's sort of what it comes down to. There are some plans to expand markets in the West. So CAISO has some plans to try and expand their market operations to include other parts of the West there. There has been some pushback, largely in that some of the policies that the California Independent System Operator wants to do are kind of forced by the California legislature, and there's some states in the West that do not like the California legislature pushing its priorities on those other states. So some of this is sort of politics around that. Southwest Power Pool is located on the edge of the Eastern Interconnect, but they're also trying to start market operations on the other side of the interconnect, which is in a sense a little interesting because they're fully not connected power grids in that they would be operating there, but that they have maybe more similar regulations, requirements, policies, politics compared to those states rather than what California has. So there's some looking at expanding that. Not much has happened in the Southeast in terms of expansion of power grids to include those areas. There was this push over the about 10 years, 1997 to 2007 really, right, where there's a lot of stuff happening and then nothing has happened since then on the expansion of markets. I know that's not an exact answer to your question, but it's people just didn't really want to is the best answer there. Yeah. So even though the markets are formed, they are not stagnant. Lots of stuff is still happening. So in 2018, FERC Order 841 was created to make some rulings about electric storage participation. So it was about recognizing that energy storage, like lithium-ion batteries, are sort of a unique resource. They're not generation, they're not load. They both buy and sell electricity, and before this, it usually wasn't allowed for a single entity to both buy and sell electricity. It had to be listed as either one or the other, and that doesn't really work for batteries. So this was a ruling in 2018 to require all ISOs to have some form of specialization on electric storage and how it can participate in energy markets. And yeah, that was only 5 years ago now, right? So it's quite recent stuff. FERC Order 2222 in year 2020 was about distributed energy resource aggregation. So if you can take all the solar panels in a neighborhood and you can call that a generator, and you can aggregate all those rooftop solar panels together and offer that into wholesale electricity markets. This was, again, a requirement for all ISOs to start implementing this process that has not been completed, I think, hardly anywhere in the markets currently in the US. And December 20th, 2023, while I was starting to make some of these slides, there was approval of CAISO's extended day-ahead market, which is to try and include some regional generators in CAISO's day-ahead market, generators that aren't necessarily within the footprint of the ISO, which is an interesting way forward for that. But yeah, so it's like the point is things are still changing. Things will continue to change in the future. And this might include more robust ways of integrating energy usage bidding processes into electricity markets. This is something about like electrochemical cells. What are more advanced ways that they could be modeled and used in market clearing models? That's something that could easily change in the future. The processes are not stagnant. So with these ISOs now, the deregulation of the electricity industry looks something like this, where the generation side is fully deregulated. So anybody can build a generator, they can connect it to the power grid, and they can start selling electricity to these independent system operators. The transmission is owned by some different entities. It can be utilities, it can be merchant operators or something, but it is operated by the independent system operator. And then on the distribution side, that is still the regulated utility that you're kind of more familiar with. This is Madison Gas and Electric, where you're charged a fixed rate for how much electricity you use. Some constant like 11 cents a kilowatt hour or something. But they have to buy their electricity from the Mid-Continent Independent System Operator at whatever the daily rate is. And their job as a utility is to not go bankrupt by buying on the markets and selling you at a fixed price. So this is sort of what it looks like within these market regions. The non-market regions that were pointed out are still this vertically integrated utility that we saw a few slides ago.
The distribution entity is also allowed to participate in battery storage?
So there's a few interesting nuances there. The question was about distribution utilities being able to sort of operate the battery. So the thing is, like Madison Gas and Electric does own some generators, but they cannot generate that electricity and use it themselves. They have to bid to be allowed to generate electricity at their generators, and then they also have to buy electricity to serve people, and there's kind of two sides to it. And yeah, so they can also own batteries that would participate on that market process, but there are rules about resources that are located sort of in the distribution grid, so like behind a substation, not directly connected to the transmission grid, that is, and that they're more or less restricted from participating in electricity markets. That FERC Order 2222 about DER aggregation, that's some of the stuff that's in development to like kind of help out with some of this, but at the moment, resources that are located in the distribution grid cannot participate in buying or selling electricity to markets. So they could use a battery that changes how much they're buying from the grid, but they can never export power to the transmission grid. There's a little bit of nuance there and hard to show without a diagram of like what that actually looks like, but there are very specific rules around sort of behind the meter electricity use for distribution systems.
But they could still use that for their pricing?
Yes, so they could use that to like sort of hedge against some of these price spikes behind the meter as long as they never export electricity to the transmission grid. Yeah. Any other questions? All right. Yep, I already mentioned those couple of bullet points there. The job of utility is to buy at wholesale rates and resell retail electricity. And that's actually an interesting thing in Wisconsin. So if you've ever tried to use an electric vehicle charger, I can't imagine many people in the room have done that. But in Wisconsin, you cannot be charged for electricity at a charging station unless it's owned by utility, because only utilities are allowed to resell electricity from wholesale markets. So Madison Gas and Electric owns an EV charging station. They can charge you per kilowatt hour. Everybody else cannot charge you the electricity use. They can only charge you for the time that you spend there, for example. So interesting nuances. This is just history of regulation that still affects a lot of the changes that are happening in energy usage today. So that's the first part, kind of fast overview of the history of it. And we're going to get into electricity markets now and how they run. So there are 7 independent system operators in the United States. All of them are also the market operators within their region. There are 2 main market types that they use, that they run. They're the energy markets and the ancillary services markets. And there are different markets with products and market types within that, but those are the 2 that we're going to be focusing on. We're going to look at day-ahead energy markets and real-time energy markets. And then we're going to take a look at the frequency, response, ancillary service markets, and the operating reserve ancillary service market. There are other ones like capacity markets, financial transmission rights auctions, and so on that we're not going to really talk about today because they're less relevant to the main topic of energy storage participation, or not energy storage, electrochemical cell participation in energy markets. There's some good industry reports about how these markets work, but they're very expensive, and I don't have access to them. EPRI, the Electric Power Research Institute, is an industry research company, basically, that does a lot of looking at all the business manuals of different ISOs and puts out reports every year about this is, 10 trends in market prices. These are changes in rules that might affect future market prices and all these outlooks and stuff. And 500 pages and $20,000 is a lot. So what I have is slightly out of date and less detailed than you can find in documents like this, but hopefully it's still fairly relevant information. EPRI does have some public reports, and that's where a lot of this information is going to be coming from. So yeah, there's these 2 main market types that they have. So CAISO is California, ERCOT is Texas. They're relatively similar in size here, so about $9 billion or $14 billion in transactions every single year on these energy trading markets. The pricing is also going to vary. You can see in that 3rd column on this table here, all-in price dollars per megawatt hour. In California, the average is $42 a megawatt hour. In Texas, it's $30 a megawatt hour. But it ranges here from $15 to $76 a megawatt hour. So there's also a pretty broad range depending on which region you're in. 2 of these markets in this list are Canadian markets, which we won't be talking any more about, but Canada also has some markets that are interconnected to the US. So there are different timings to different aspects of the electricity markets, and we're going to be really talking about this day ahead and real time. So day ahead is 1 day prior to the actual time at which stuff is going to be generated, and real time is every 5 minutes, the day of. And that's the time that we're going to be taking a look at. There's longer term things like capacity markets, forward markets, that we won't be talking about today, but they are relevant to more general market operations. So energy markets, what an ISO more or less does is they take bids from generators on I'm willing to sell electricity at this price, and from utilities that have to buy electricity to serve their customers, and they just find the intersection of we need to buy a gigawatt, who's going to sell me the cheapest gigawatt, and there's your clearing price. The main thing to know here about how these markets work is that whoever gets chosen to generate electricity, so these are all the generators that bid less than the clearing price, they are all paid the clearing price. They're not paid what they bid. So in the example here in this top row, we have what's called a merit order curve here. So this is along the x-axis, this is the capacity, and the y-axis is the price. So the orange in the bottom left there, that's renewables. There's the width of that orange bar there is how much renewable energy capacity was bid, and the price is fairly low because renewable energy is very cheap to generate. You're not burning any fuels you have to buy. Then there's nuclear, and in this figure, the next one is different types of coal, and then the clearing price is halfway through that light gray bar there. But the lower figure there shows that what if there's more renewable energy that day? It shifts over all that capacity, and now the clearing price is going to be cheaper because there was more renewable energy. This also means that renewable energy is going to be paid a lower price because they took over larger portion of that market that day. I want to give a little sense of scale here, because not everybody here spends time looking at electricity numbers and what orders of magnitude that we're looking at. So what we'd be focusing on today is, like, the largest wind turbine. That's something that's like around 15 megawatts of electricity generation. A typical nuclear power plant, coal power plant, these big facilities are going to be around a gigawatt. Average power usage in the entire United States over the course of a year is 450 gigawatts. So every second, on average, is 450 gigawatts of power usage. So everything that we're going to be talking about today is sort of within this range. Let's do a quick example here on what is the clearing price of electricity. So this is for your participation here. We have a generator, G1 here at a substation. It costs $25 a megawatt hour to run. We got a power line connecting to another substation where there's another generator and there's a utility buying some energy, right? So if G1 is $25 a megawatt hour, G2 is $40 a megawatt hour, the demand is buying 100 megawatts, and that power line can transfer 150 megawatts across that power line. What's the cheapest way to generate electricity to serve that load? Everything should be generated at G1 for $25 a megawatt hour. Yeah, it's pretty cheap. There's no physical constraints on the system that are going to change what that minimum cost dispatch is going to be. If we reduce the capacity of that power line to 50 megawatts, now what's the cheapest way to generate all the electricity that we need? Yeah, I think I was hearing the right answers there. So yeah, G1 would be able to generate 50 megawatts and send that across that power line, that transmission line. G2 would generate 50 megawatts as well, and all of that is going to serve this load at substation 2 there. So in this problem here, G1 is paid $25 a megawatt hour because that's the... I'm going to introduce this a little bit more, I think. I'm going to start with substation 2 first. So at that location, I'm going to start talking about marginal prices now. Locational marginal prices, because one of the things that happens on the power grid because of constraints in the network is that prices are going to be different in different locations as a result of those constraints. So what we're going to talk about here is locational marginal prices. And the marginal price is going to be what is the cost of one additional megawatt of power at some location in the grid. So starting at D2 here, if D2 was instead buying 101 megawatts, that next megawatt would come from generator 2 at a cost of $40 a megawatt hour. So the marginal price at substation 2 is $40. At substation 1, if one additional megawatt was consumed at substation 1, you could get it from generator 1 and it would cost $25 a megawatt hour. So these two substations have different prices on the cost of using electricity in these locations. So what that means is that the marginal price at substation 2 is $40, so D2 has to pay $40 times $100 of megawatts of consumption, so $4,000 in this example. G2 is paid $40 per megawatt hour for the 50 megawatts they produce, 2,000, and G1, this example is wrong, I'm sorry. G1 is actually paid $25 at that location. So I will update the slides and send them out again later. But the G1 is paid $25, not $40, because the marginal price at that location is $25. So where does the extra money go? D2 paid into the market more than G1 and G2 got paid out of the market. The remainder there goes to whoever owns the financial transmission rights to the power line. So the congestion revenue, this cost difference effectively of congestion on the power line, goes to whoever owns financial transmission rights to the power line. Those are something that are sold at auction that I kind of glossed over before, but this is where some of that extra money goes as we have these price differences that can come up from the constraints in the power grid. The next example here I think was a better way of showing that. Now we have two loads on either side here, and we have the same constraint on that power line. So I think this is pretty similar to the previous example, except now we have an extra 100 loads at substation 1, so 150 megawatts generated by G1, and we have 50 megawatts generated by G2 to serve those respective loads. And we have the same marginal prices in this example here. Question?
So I'm a bit confused.
Yeah.
When you said about the merit order, did everyone get paid at a clearing time? Market clearing?
Yes. So that is when you don't have any physical constraints of the power grid. So in a sense here, so that clearing price is now the clearing price within each substation is one way to think about it. So everybody at a physical location will be paid the same price or pay in at the same price for electricity usage. That merit order is a way of like looking at the broader sense of the power grid and all the generators. If you had no constraints on the power grid, that clearing price is what shows up. In this case, we have different clearing prices in different locations of the power grid. It's the difference.
So,
Yeah.
the assumption is also that this marginal cost of production is known to the market. So everyone has given their marginal cost of production.
Yes. Yeah. So in this case, it's the generator's bid into the market, and their bid amount. If they are the marginal generator, their bid amount is the clearing price.
Okay. And then you said the extra money would go to whoever owns the transmission for the congestion.
Mm-hmm.
So then, I don't know how to phrase this, but then what's the incentive for them to decongest because they get paid?
Yes. Yes. So it's not specifically whoever owns the transmission line. It's whoever owns financial transmission rights to that power line. So the system operator at the start of every year and then at the start of every month, and potentially at the start of a season sometimes, they will run an auction for people to buy the financial transmission rights to a transmission line or a set of transmission lines. And generally what will happen here is that a generator will buy that and use that to hedge against congestion that would limit what they get paid for their generation. So it's not the transmission line owner. I guess anybody can buy these, including financial institutions that then resell them with bilateral contracts and so on. But anybody can buy those, and typically it's the generators who would be affected by congestion that use that as a price hedge so that it can be paid money even if there is congestion that will limit their generator price. Another question?
I assume there's some regulations in place to avoid conflict of interest there, as far as, I mean, if a generator owns it and they do, I mean, they probably don't have as much of a direct effect, but as far as influencing or lobbying to or working towards, better energy solutions,
Mm-hmm.
would there be any kickback to that? Have you seen anything
Yeah.
of that sort? Or?
Yeah, so yeah, the question about conflict of interest of generators also owning transmission rights and how that works out. So there are challenges of stuff like that on the power grid. There typically are regulations. On the generation side of stuff like this, so there's a few processes in place to prevent market manipulation. So depending on the type of generator, there are different processes for this, but essentially if generators seem to be bidding out of line with their actual operating costs, they are typically fined, and if they do this repeatedly, they are kicked out of the market. You have an asset that is not allowed to sell electricity anymore. That's bad for them. So there's incentives within the market system to keep generators honest about what their bid prices are actually their marginal prices within the market. And then the financial transmission rights are just financial hedge for the companies that would own these generators so that even when there is congestion, they will still have some revenue, in this case from the congestion instead of from generating electricity. But yeah, not really an issue in that sense. Yeah.
So could you go back to the previous slide?
Yeah.
So effectively, G1 is still paid at 40 because they initially get paid 25 and the rest of the money goes to G1, assuming that G1 owns that.
Yes, if G1 owns the financial transmission rights to this power line, they would, in a sense, be paid that full amount because they're paid $25 for the electricity and then an additional $15 for the congestion, which is $40. Yeah. So they're effectively pretending to sell the electricity somewhere else in the system, is what that gives them.
So you said back again?
Yeah, they own it for a certain period of time. So the annual auctions are to purchase the financial transmission rights for 1 year to 3 years at a time. The monthly is another auction that happens for anything that wasn't bought for the annual process that people can then buy for a month at a time in those auctions. Yeah. This is the last we're really going to talk about financial transmission rights. We're going to talk a lot more about LMPs because that really affects how you buy electricity at different prices in different places. But we're not going to get too much into this because FTRs are a very confusing topic. And it takes a while, like actually sometimes looking at the math to understand what some of that process is. And it's also not really sort of a physical process of the power grid, it's financialization of it that's happened, and it's a bunch of non-engineers have gotten involved to make things even more confusing for us. The last example, this is actually going to get into more the physical problems of operating the power grid, is what if you actually have a network, not just a point-to-point line? So the idea here is that now you have to respect the physics of the power lines when you're choosing what generators get to generate power. So in this example here, where we still have line 1 here has a capacity of 50 megawatts, the other 2 lines also have a capacity of 50 megawatts. All 3 of these power lines have the same resistance value, we'll just call it R here. The question now is how much can you generate at G1, and then how much will you have to generate at G2 or potentially G3 to meet demand? Again, the only demand again is going to be substation 2 there has 100 megawatts of demand. People are thinking about this one. The thing that I really wanted to emphasize here is that on the power grid, you can't actually choose exactly how much power goes down a specific transmission line. It's all about the physics of the network that result in how the power is going to flow here. So in this example, line 1 has a resistance of R. The path that goes from line 2 through line 3 has a resistance of 2R. Each segment there is resistance of R. So what that means is that we will have twice the power flow down line 1 as the route of line 2, line 3 when we generate that electricity at G1. So just because of the physics of the system, that's how it's going to flow. So that means that we can at most generate 75 megawatts at G1 because 2/3 of that power will flow down line 1 and 1/3 will flow the other way, right? Twice flows down the first path and half of that down the second path, which means we're limited to generating 75 megawatts, even though you could theoretically generate 100 megawatts and send 50 down one and 50 through the other loop. Because of the physics of the system, we do not directly control the amount of power flow on every single individual power line. It's the physics of the system based on where electricity is generated. So in this example, G1 is limited to 75 megawatts, and then G2 will generate the other 25 megawatts. People tend to be very surprised by some of this and how the power grid is limited by physics, but it's not like the internet. You can't just choose where packets flow. It's complicated. You have a question, Adam?
Yeah, just one more thing, sorry.
Yeah.
For lingering on this, but so is this? I've heard of cases where they've just had to ground extra electricity, or for price reasons, or go down to negative prices. That's probably some of the reasoning behind that option, I would assume.
Yes. Yeah. So talking about sort of like about curtailment stuff, right? So this is particular for like renewable energy, where like it could be generating more, but the power grid can't actually accept more because of things like transmission constraints. And that would then limit how much of that can actually be used. We'll talk more about curtailment in the last half of this. But yeah, so one thing to know is that we can't have negative prices because generators bid negative amounts. Some of that is production tax credits for renewable energy that they get paid. Even when if they get paid and the power grid prices are negative, their tax credits still cover that and give them some profit. So like that can be a part of negative pricing, is that wind especially is willing to bid fairly negative prices and they will still get paid out. But it is possible to have negative prices even with no negative generator bids. And that is just the broad issue of congestion on the power grid. Negative prices result from there being sort of this, I'm blanking exactly which one, but so the economic surplus is improved when a certain location consumes more energy, And therefore, they would have negative prices because it would mean that if you use more energy, it lets a cheap generator generate more power, an expensive generator generate less power, and now the total amount of money spent on generating electricity is lower, even if more energy is being used. That is a process that can result in negative prices, even without negative bids for selling electricity. So there's a few processes separately that can all cause that. There are some good examples that I've seen, but I cannot come up with on the spot because they have to like really mess with the numbers to make some negative prices happen. But yeah, negative prices. We'll also be talking about that in some of the data parts about what sort of times of the year, times of day, and stuff that will typically result in lots of negative pricing. Real networks are also bigger than 3 power lines, typically. So this is a model of the California power grid that my research has been creating over the past couple of years. So in this network, there are over 10,000 substations, over 15,000 transmission lines, and 3,000 generators. So nobody's actually looking at an Excel spreadsheet of all the numbers and doing this. This is where we use mathematical optimization in order to solve these problems, because they're going to be very, very large. So what we can start to take a look at now you understand some of the basics of this, is what do LMPs actually look like in different parts of the United States. So this is the Mid-Continent Independent System Operators region. It's colored in according to the sort of pricing of electricity within their service region here. So it's the cost of an increment and 1 additional megawatt of electricity consumption. Because of some nonlinearity, increment versus decrement actually makes differences in how pricing would work here, but this defined as an increment in electricity usage. So the results from, the cost of the cleared generators, what they bid, then there's additional costs related to the congestion, which change that whole market clearing price to be related to congestion on the market, and then cost of losses on transmission lines. We haven't looked at that, but there's energy losses on transmission line, and that will also affect some losses of only 99% makes it to the other end. Might have a slightly different cost of electricity as a result of those losses. And these can be very, very volatile. So I was looking at some of the prices last week when I was finishing the slide. So some interesting stuff was happening on January 4th here. And you can see a big price difference between MISO North and MISO South. So there's a capability of 2.5 gigawatts of power transfer between MISO North and MISO South. And here it's running at capacity, and there's still a price difference across the 2 regions. The marginal price on the north side is roughly around $40, slight variations in the region right. In the south, it's about $20. This was at 3:30 p.m. And 5 minutes later, this is what it looked like. We're at $160 now. So in 5 minutes, we went from $40 to $160. And again, so this is just the marginal price at this point in time. There was something happened, caused a bit of a shortage. We needed some generators to ramp up. Not many are available. Only the really expensive ones are available. And the price went up. And 10 minutes later, it was at $400. So now we're at 15 minutes. We're at 10x the price over the course of 10 minutes. Like, this is how fast electricity prices can change. When something goes wrong, there's congestion, there's not much available reserves, prices can start to go crazy. And 5 minutes later, it's back down to $40. Stuff can happen really fast on the power grid. I was looking at some of the dashboards from MISO, and the best that I could tell is that there were a higher number than expected of offline generators, maybe like down for some emergency maintenance or something. There's also very low wind power on this day in Iowa, in North Dakota. So that probably resulted in like the higher prices already at 3:30 p.m. But then in the course of these 30 minutes, there was a full gigawatt of wind power that was lost. And now we had to make that up. But the grid was already like kind of straining a little bit with unusual conditions, and that just caused prices to skyrocket and then settle back down after 10 minutes. So if you're buying electricity in this sort of a system, you really want to stop buying for like 10 minutes and then be able to buy it back again, so that you aren't subject to these sometimes skyrocketing prices that can happen. Any questions? This is also pretty typical of Texas. Yeah, question?
Are these slides going to be available afterwards?
Yeah.
Okay.
Yeah.
Oh, it's already in there. Oh, sorry.
This is a bit extreme, but this is what you can kind of see in Texas, is that the Panhandle in West Texas has a lot of wind power, but it's pretty far away from the load centers in Houston, Dallas, Austin kind of areas. And the result of that is you can get some very low negative prices in West and Panhandle, Texas, and high prices in those load centers because there isn't enough transmission capacity to move power between those regions. So these prices are a bit extreme. They go down from about negative $40 up to $5,000 here. The Texas market is much more extreme in pricing than the other markets. So 5,000 is high, but happens several hours a year in Texas. Yes?
I'm just curious, how is the cost of congestion really different?
It has to do with it's just the price differences between two locations is then the price of congestion. So on either end of a transmission line, whatever the marginal cost is, the price difference in that marginal cost is then the price of congestion across that power line. The idea being that you can get electricity from a generator or from a power line, whichever one is cheaper is one you should use. In this case, you're limited by the capacity of the transmission line. So that price difference is now the price difference across the transmission line. So that's where you see these very sharp price difference lines, like right up here. That's just like either end of a transmission line where it's negative and positive prices. You will typically have these very sharp price changes when it's a transmission line that is congested. Within West Texas here, this seems to be more about just is enough demand for electricity and some of the losses are taking over, but this is specifically a congested power line up in the north. Turn that off. All right. So that's mostly about the geographical constraints. The other thing that can happen is temporal constraints. So ramping capabilities, changes in electricity usage throughout the day that will lead to lots of different price changes as well. So the example here is in California, talking about net load. So net load is the amount of energy demand minus the amount of solar and wind production at that point of time. So this is called the duck curve here. It's, in a sense, because it looks kind of like a duck to some people. What this is showing, though, is the energy demand minus all the renewables, which in California is lots and lots of solar. This is, in particular, showing the lowest net load day. So this is sort of the worst day of the year for this effect in California every year. And each year it is getting worse. Right, so in 2015 is that top line there, but as more solar, especially distributed solar on people's rooftops has been installed, this number just keeps getting lower in 23. I mean, we hit below zero for about 5 minutes there, where more renewable energy was being generated than all of California could use. What this means is that when that solar goes away and you actually hit the peak load point of the day at about 8 p.m., 9 p.m. here in California, you need to somehow ramp up 20 gigawatts of generation in 2 hours. And that's a big challenge. That's a lot of thermal stress on generators to spin up that fast, heat up that fast if they are turned off. A lot of generators have minimum capacities, so you cannot be on and below a certain amount, right? So it has to be offline, but then turning it online and then get ready to ramp up is its own challenge. If you have to keep it online, well, now you're not using that solar panel in the middle, all that solar power in the middle of the day. You have to run these generators at their minimum capacity in order to be able to ramp up. And depending on the technology, there'll be about 1% to 25% per minute capacity that they can ramp up. Generally, it's expensive and inefficient generators that can ramp faster, which isn't great exactly on the emission side either, and definitely not on the cost side. So the main idea of being able to meet peak demand is that you have a lot of base load, you have different generators maybe that are slightly higher cost, they won't run as often, but they can ramp faster, and that's where a lot of natural gas combustion generators are able to fit in, is sort of these peak load kind of scenarios. The challenge here is that sometimes they cannot ramp fast enough, or they have these minimum off times, and then they have to stay on even at a minimum, and that causes prices to rise as a result. So on the left side of this figure here is sort of this ideal case where this orange generator starts up and runs, and then it turns back off. It's a short amount of time that it's actually running for. It quickly turns on and turns back off. In reality, it might need to start up a little bit earlier in the day so that it can warm up and then be ready to ramp up to that peak capacity. But by turning on earlier, it requires other generators to have to turn down their output power. Even if they're cheaper generators, even if it's renewable energy, you have to maybe have some curtailment to be able to have the capacity available in these natural gas generators to ramp up to that peak capacity. You also have some generators, so this is typically these big like nuclear or coal power plants, it takes like 24 to 48 hours to start up. It's like a long time. So the screen generator that's being shown on there, it cannot turn off overnight, even if it's uneconomic to run overnight. So it has to stay on in order to have that capacity for later in the day. And that also will cause other generators to have to reduce their output in order to meet the reliability of the daily changes of electricity usage. And yeah, there's startup ramping constraints on startup and shutdown costs. And these really combine together to create some challenges in running the grid when you have these lots of resources that change their output throughout the day from renewable energy. Energy demand can also really affect that a lot in terms of electricity usage. And these are places where a lot more energy storage or responsive demand that will use less electricity as it gets more expensive, which can be due to the ramping. Responsive demand can reduce what those peaks actually look like. And it's going to be sort of interesting how that plays out into the future. Lots of storage is being built. There's a report put out today, actually, that they expect next year to increase the amount of battery storage on the grid by 90%. So we're going to go from about 16 gigawatts today to 30 gigawatts next year of batteries. And a lot of acceleration happening on that front to meet some of these challenges that are especially happening in Texas and in California. All right, it's been about an hour, and the next bit has some math, so I think we should take a 5-minute break here, and then we can come back. All right. Let's get back into it. So settling energy markets. We've kind of talked about is how prices end up forming in it, but what does the market operator actually do to settle the market, respecting all the constraints of the equipment and stuff? So the main things that the market operator gets is going to be cost bids from all the generators, what they're willing to generate power at what price. And then what are called load-serving entities, which are these utilities that buy electricity. A load-serving entity is anybody buys electricity from the markets. And it's more specifically the purchase amounts, and they tend to be irrespective of price. We buy 100 gigawatts because people are buying electricity, not if it's below a certain price, we'll buy it and we'll cause blackouts if it's below that price. They're not allowed to do that in a sense. So some demand can be price responsive, but generally hardly any of it is. So to do this, like I hinted at before, we use mathematical optimization. We're not going to dive too deep into what the constraints of this look like, but the cost function here is to minimize the cost of buying electricity on the market. So the cost times the amount of generation from each of the generators is that top bit. And then there's a few constraints that we would have in here. So conservation of energy at every single location in the network. So what is generated by generators, what gets used by loads, and what's moved along transmission lines has to sum to zero at every location in the network. We use a linear approximation of the physics for power flow, which is that gray equation there, 1C. And then there's some things like engineering limits. So you can only have so much power flowing down a power line. A generator is between its upper and minimum power outputs. And then this optimization problem is solved for mostly that variable PG of how much should each generator generate. The dual value of constraint 1b determines the locational marginal price. This is sort of what accounts for all the congestion in the network, the pricing of the bids and so on is going to be the dual value or shadow price of this constraint. If that doesn't mean anything to you, that's all right. That's mostly an optimization term. There can be extensions of this problem that we can also take a look at. So we can do multi-time periods in this as well. So now the objective function, we're also going to sum over time, say 24 hours in a day, right? And now we'll have some ramping constraints down here as well for how fast can a generator ramp up and ramp down and to change its output throughout the day in response to demand. And again, if this gets constrained, it means that generator cannot output more power and it has to come from somewhere else in the network, and that will change the clearing price within the shadow price of different parts of the network. An important part of this generator minimum is actually that we don't want all generators running at all times. So we also add this binary variable of what generators should be on and which should be off for the entire day, typically. So in the objective function now, we now have this other term here for the startup costs of a generator. It costs them money to start up. They have this minimum output for a certain amount of time, not serving load, and so on. So that's captured by what's the cost of turning it on. And then in some of these generator constraints now, we have them multiplied by this binary variable of whether or not the generator is on or off that day. If it's off, it has to output be between 0 and 0, right? Cannot output any power. So the result of what this is now that we'd be looking at is a mixed integer linear program. And it's determining how much from what generators should generate power that day. These can become very, very large problems when we're looking at large power networks on the power grid. So I set up this as an optimization problem, moderately sized replica of a power grid. So this is about 13,500 substations or nodes in the network of a power grid. Here, this one's about 20,000 power lines, 4,000 generators, and we do this for 24 time periods. And the results is that we have a mixed integer programming problem that has 841,000 constraints and 591,000 variables, with about 97,000 of them are binary. So this is a big optimization problem that we have to solve multiple times a day for each ISO in the power grid. And this is still sort of a simplified problem, like the actual problems are going to be bigger than this, and this is the big challenge of what the market operators are doing is like, oh, now we have to add energy storage to this. What other kind of constraints does that have? That'll also have some binary variables. Is it charging or discharging at different times a day? So these are really big, hard to solve optimization problems that have to be accounted for by the market operator. So they use variations of these three different optimization problems in different parts of the market. We'll come back to this slide and the rest of the wall of text here, but there are two main markets on these energy market side. There's the day-ahead market and the real-time market. So this day-ahead one uses this most complicated version of the problem, uses this unit commitment with hourly resolutions. We have 24-hour time periods in here. The real-time market is what's going to be solved every 5 minutes during the day, and this will solve this single time period. Typically, some markets use a multi-time period for like a 1 hour horizon in real time, but without the binary variables, because you can't solve that problem fast enough to resolve it every 5 minutes. So the process of this day-ahead real-time market is what I'm going to talk about next, and then we'll get to other bullet points on that slide. So energy markets, there are two settlement markets. That doesn't mean we run optimization twice a day. It's multiple times per day, but I'll talk about some of this process here. So the question is, who gets to generate electricity right now? And how did that decision get made? So the start of it is the day before the day-ahead market was cleared. So by noon that day, market members will submit their bids for how much electricity they want to generate and the prices, how much they're going to buy. That optimization problem is solved, and by 4 p.m., the market is cleared, and the hourly schedule is then posted, which will be starting at midnight. So this is the first financial settlement. Whatever gets selected at this time, people will be paying that price for buying and selling electricity, and additional stuff will be happening real time for the additional changes in electricity production. In the real-time market, this starts at midnight. 1 hour before the market process is going to happen, market members can stop updating their bids, which is to say they can continuously update their bids all day long. And especially energy storage is going to do this. If they want to be cleared or not be cleared in the market, they'll shift their prices around. Also for wind and solar, they'll update based on their forecasting as it gets updated, how much electricity they're going to be selling in real time. So 5 minutes beforehand, the market gets cleared. We have one of these optimization problems. This is the second financial settlement, and this is the fixed then generator output of what they're going to generate right now. It's the sum of what was cleared in day ahead and in real time is what they will be paid for generating. And the way that this works with these two financial clearing settlements is that whatever they get cleared for in the day ahead, they'll be paid for that amount, say $100 at $30 a megawatt hour. If they generate an additional 20 megawatts in real time at $40 a megawatt hour, then they'll be paid additionally for that. And you sum that out, divide it turn megawatt hours into megawatt minutes, and you get $31 is what they're paid for this 5 minute window in time. Does this make sense? This two market clearing, this two-step process. Yes?
So what happens if like generator one commit to generate 100 in the day-ahead market, but it cannot generate that many?
Then they have to buy back their position in real time.
Okay.
So,
You need to guarantee 100.
mhm. So there are, in the energy market, all they have to do is buy back their position. In capacity markets, there's additional sort of penalties that happen for that, but we're not talking about capacity markets, so that's not part of this here. On the energy side, it's just buying back their position. So they have to buy 100 megawatts in real time at whatever the cost is for doing that, right? So they are paid $30 per megawatt hour in the day ahead, and now in real time it's $40, so they lost $10 per megawatt by doing that, right? The other thing is, if it's cheap in real time, they can not generate, and then they pay back their position at a lower cost than they bought it for, and they make more money now this way, right? So this is how some of the prices will affect their behavior in real time. All right, so back to the wall of text. So these are some details that might be relevant, and this is mostly, again, context kind of information. In the day-ahead market, it's solving this generated dispatch for the next day. We use this hard-to-solve mixed interlinear programming problem, the unit commitment model. One thing that can also happen here is we have virtual trading. So this is another, like, you can not own a generator and buy electricity and then sell it back in real time, right? Virtual trading is also a part of these markets to increase liquidity. It does also allow price-based demand bidding, but that is not a very large amount of the demand that's a part of electricity markets. It's mostly because it's utilities that buy electricity and sell that to their customers as retail rates like Mass and Gas and Electric, but Mass and Gas and Electric doesn't get to control how much electricity you use most of the time. So demand response is usually a pretty small portion of that. Bids close in the morning, results post in the afternoon based on the results of this optimization problem, right? The real-time market, it starts at midnight and it's solved every 5 minutes all day long. This is an updated amount of generator output, an updated generator or energy usage by utilities. It will also be affected by things like wind and solar forecasts changing throughout the day and how much that affects energy balance in the grid. So maybe you need more generators that are gas or coal generators to generate more power, and that might cost more money than during the day time if forecasts were wrong for wind and solar. Again, you can update these bids up to the hour beforehand. There's a question, Adam?
Yeah. And so when we're talking about solving for real-time market,
Yeah.
I'm assuming that's a somewhat different model than what we're using for day-ahead market, right?
It is a somewhat different model, yeah. So it was the first model that I introduced there, which is just this one time period power flow problem, linear programming problem, right? Some regions do use a multi-time period problem where they solve with a 1 hour horizon with 5-minute intervals, but no binary variables in the real-time market optimization problem.
So they have to, okay,
Yeah. Demand response can act as a supplier. So this is the idea of you bid as demand response to generate electricity by not using as much electricity, but you can put a price to that as you bid in. The virtual trading doesn't happen in real time because that's where the virtual trading gets settled at. And then again, the price you paid out in real time is your deviation from what you were charged at the day ahead market. So you generated 20 more megawatts, that $20 megawatts times real time price is what you get paid in the real time market. There are different names for everything in different ISOs. So this is a table of some terms you might see related to day-ahead market. Most people do call it just day-ahead market. In California, it's called the integrated forward market. We're only talking about energy, but there can be other market products that get cleared in day-ahead market. So these can be co-optimized. These ancillary services are typically co-optimized in day-ahead. Not everywhere, but in most places it is. The day-ahead market closing and posting times vary quite a bit as well. And then this reliability unit commitment is something we're not really talking about here, but this is a step to verify that the market clearing is actually physically possible on the power grid by solving a more realistic model of the physics of power flow and make sure that it's still feasible, because the simplistic version of the physics in the market clearing problem doesn't account for everything. So this is a reliability check on it, and if it fails, then they adjust some things on the market to be able to get a market clearing that is physically possible to do. The real-time market has more variation in pricing here and more variation in steps. So mostly it's called this real-time market, and everywhere it is solved every 5 minutes. Most regions use single time period, some use multiple time period. So that's going to be New York ISO and California ISO use multiple time period optimization problems here. There's a different forecast horizon that they use on the rolling horizon aspects of that. And sometimes they do use a unit commitment with a 2-hour look ahead. So not at a 5-minute interval, but at a 2-hour interval, they might change and like add new generators, get them started up so they can participate 2 hours into the future. So there's, again, some variations in here, but overall, this is the real-time market terms that you might find in places. So to summarize energy markets, a question first.
So these prices are distributed to all consumers equally, or so hypothetically, if there was a case that, say, a factory was planned for a shutdown next day, and because of their economics, they decided not to. So now that impacts so because of which the day-ahead market was settled in a certain price, but my real-time market gets jacked up because they are still consuming, and that price is now distributed to all the consumers?
Yes, so sort of a question of like, if there's a big energy user that changes how much energy they use, that will affect energy prices, and that also affects every other consumer of energy and how they will, So yes, that is, I believe how you describe that is accurate, right? Like, the big industry user uses an extra gigawatt of power, that gigawatt has to come from somewhere, it probably causes prices to rise, and so real-time prices will go up for everybody. But other users will only pay the difference in energy usage from what they bought in the day-ahead market, right? So if a utility buys 100 megawatts from the market day ahead, and they use 100 megawatts in real time, they don't pay the real-time price at all. If they consume an extra megawatt, they pay that in real-time price. If they use one less, they get paid back effectively at the real-time price for, again, the buying back the position kind of thing, right? So yeah, it's not exactly market manipulation, but like, yeah, the big industrial user can affect the prices, but if you only use what you bought before, it doesn't really affect you. So yeah, summary of the energy market side of things. Again, generators and load-serving entities are bidding these price and energy amounts that they're going to buy and sell. The ISO market operator uses a big mathematical optimization problem to figure out what the clearing of the market should be, what every generator generates. The prices are determined from the marginal generator, and then that can come out from the optimization problem as the shadow price of the energy balance equation. And that price will be affected by, congestion on the power lines. You have these variations in time due to the ramping constraints that can be affected by it. We have these 2 financial settlement periods, but the optimization models are run multiple times per day, depending on, if reliability was affected, they have to rerun it for certain reasons. And also the fact that in the real-time market is resolved every 5 minutes. So that's energy markets, ancillary services markets. These are additional market products that support grid reliability. It's like sort of reserves in the system so that if a generator goes down, if more energy is used than was expected, you have reserve generation available that can quickly respond and generate more power on the power grid. These are typically going to be co-optimized. So the same optimization problem will include this. Generators would bid both an amount of energy that they could generate as well as an amount in some of these reserve products so that they can offer. They might get cleared for both, they might only get cleared for one or for nothing, right? So this is some of the aspects of the decisions that a generator would make on how they bid into the market for providing these services. The 2 categories we're going to talk about are regulating reserves and operating reserves. Operating reserves also has 2 subcategories of it, of spinning reserve and non-spinning reserve, and this has to do with, is it an online synchronous generator connected to the power grid, or is it something else? Is it a generator that's off? Is it a battery? Synchronous generators are, the big spinning turbines that are completely synchronous with the power grid. They're able to respond a lot faster and more effectively, and for that reason, they have 2 different products there that will have different prices as a result of their responsiveness. So There are other services that I'm not going to talk about for a few different reasons. Some of them are specific to only certain ISOs. So for example, flexibility reserves is something that Mid-Continent Independent System Operator and California Independent System Operator both have, but no other markets have it, so I'm not going to talk too much about that. Some are things that are required by regulation, so they're not market-based, they're not done through market clearing. Other ones are done through cost-based recovery instead of market systems. And then other ones, like inertia service, they're just naturally provided by the physics of the equipment on the power grid, and as of today, we don't need a market incentive to add that to the system. If we get an entirely renewable dominated power grid, that might change because we lose the inertia of these big spinning equipment generators that are able to ride through very quick faults on the power grid. So that spinning inertia of just having a big turbine is a valuable service that we have today that we don't pay for, but we might be doing that in the future. Regulating reserves are the first one I'm going to talk about. These are the very fast frequency response that is necessary to maintain the grid frequency at a stable 60 hertz that we have in the United States. So they're required to respond between 2 and 6 seconds depending on the ISO. And it's these very fast response for quick changes in energy usage or in renewable energy generation that might happen. They might be separate market products of regulation up and regulation down if you're increasing or decreasing energy usage in the system as a result of that. They have a minimum duration, typically of about 15 minutes. If they're called on, they run for 15 minutes. This is sometimes necessary for equipment that cannot quickly turn on and turn off if they have a minimum runtime and so on. So not that much energy is procured in this, or not that much amount is procured. It's not energy, it's an ancillary service, right, in each market. There's some specific rules on markets. Sometimes it's a fixed amount, sometimes it's based on the forecasted load and renewable energy in the market, and it varies a lot. But the average amount across all these markets is about 300 megawatts every single day. These markets are usually like tens of gigawatts in size on the energy side. So a very small amount of that is needed for this regulating reserve frequency response type of product. The prices for this in day-ahead clearing are typically around $15. In real time, it depends on the market, between $10 and $25. So the way that this works is that they are paid for being available. And then if they do generate electricity, they are also paid the real-time price for the energy that they also produced. But this amount is just for being available to generate electricity if needed. And if they're supposed to do it and they don't, they get penalized for not being available when they said they would be. So these are the most valuable reserve products that exist in the markets. The other ones are worth a lot less than this. So this other category is called operating reserves. The previous one was like 2 to 6 seconds. This is 10-minute response time. So slower, but generally most traditional generators would have to be running in order to start up fast enough to provide this. Batteries are a good resource for providing this fairly quickly for non-traditional resources anyways. So again, a few different names depending on the market region, both on the spinning reserve side as well as the non-spinning side. Minimum dispatch when this is called on is 60 minutes everywhere except for California where it's 30 minutes. In ERCOT is non-specified. So also PJM is 30 minutes. So most common, I guess, is 60. The purpose of this, again, is like ramp up within 10 minutes to be able to provide energy to help stabilize the power grid. The prices, I believe, no, next slide is how much. So depending on the market region, again, it'll vary on the rules that they have for it. Typically depends on amount of renewable energy, especially wind, and the expected load for that day. But depending on the market region, it's going to be between about 1 and 4 gigawatts of operating reserves every day. So this is closer to like 10% of the market size. Question, Adam?
So is the general consensus that the incentives for, because I know that we are seeing that there are a lot of there's a lot of cases of isolated power and large pricing gaps and stuff like that. And so is the general opinion in the ISOs that whatever the regulations or incentives for ancillary services right now is not enough, or
No, so that really won't be much of an ancillary services issue that causes that. That's almost entirely going to be transmission lines not being a high enough capacity to move that power. Yeah, that'll be where a lot of that curtailment is forced, is through transmission line capacity rather than stuff like ancillary service availability. Yeah. Qualifications, how do you qualify for being an operating reserve? There's some rules about that. Again, they're different in every ISO, and they're spread across all kinds of different documents. But there are some specific rules in here. For example, in PJM, storage reserves are set to 0. They cannot participate unless they get specifically qualified under non-spin resources. Similar thing in MISO, that they are not spin qualified, and there's separate stuff about dispatchable resources being ineligible. So very specific legal documentation gets into whether or not a resource qualifies. It's not necessarily an engineering reason. It is typically hard to find these details sometimes as well. So worth knowing potentially how to find that if it's something you're interested in. Oh yeah, I mentioned distributed resources and how they might participate. It can be restricted in some locations. Prices here are a lot lower. So spinning reserve is about for $5, and non-spinning is going to be about $2. So a lot less than like the potentially $25 you can have for the fast frequency response. That's going to be about it for market operations, market products. Next up, we're going to be talking about how to participate, how different resources might participate in markets. Any last questions before we move on to that? All right. So how does a generator participate in markets? They have a few different ways that they can bid into markets. They can do block-based bids. So that's going to be the sort of that step function you can see on the graph there, where they just like bid this amount at this price and then another amount at some price, and it's just a step function between those is what they bid in the market. The requirement is that it's convex, but that's about it. They can also do sort of a piecewise linear pair of these similar bids. And then an interesting one is self-scheduling. So they tell the market, we're going to generate 800 megawatts tomorrow no matter what the price. It sounds crazy, but typically this is going to be resources that don't think they're going to be flexible enough to be able to respond to how the market tells them to respond. So this would be things like a big nuclear power plant that can only ramp up and ramp down so quickly. They would try and avoid that. They also have very low operating costs, nuclear power plants, so they kind of just want to be clear no matter what, so they never have to ramp down. Even if it's going to be negative prices for an entire day, they don't care, because then it can be at full power the next day. So because they don't have to spend money on the fuel, for nuclear fuel, it's very cheap relative to the capital cost. They want to run 100% all the time. They'll just bid a fixed amount of electricity. Another example is cogeneration plants. So like these industrial users that built a power plant and they also use that process heat, well, they want to run their factory, so they want that coal power plant to run no matter what. And as a result, they will do a self-schedule, a fixed amount of energy generation for that day to have enough process heat to run their facilities. These can cause weird things to happen on the markets. For example, Southwest Power Pool, about 50% of the energy is self-scheduled, which is one of the reasons that leads to a lot of curtailment, is like all these generators just like, no matter what the price, will run. And then you can have very low prices where it causes wind curtailment, and it messes up with a lot of the market dynamics that can happen there. So it depends on the region how much that happens. I think Southwest Power Pool is the worst case in terms of the amount that is self-scheduled. So if you're a natural gas turbine generator, you exist to turn natural gas into electricity. And natural gas is kind of interesting then, because you're participating in two different commodity markets at the same time that also have fairly different time scales associated with how the prices change there. So say you're buying natural gas at $2 per MMBTU, you convert that into electricity at about $7 MMBTU per megawatt hour. That means that as long as you sell electricity above $14, you cover your fuel costs. They'll try and do more than that to cover the rest of the operating costs and then capital costs of the facility. But this number here, sort of that ratio of, or multiplying the efficiency by the natural gas cost, is called the spark spread. It's common enough that people use that when analyzing prices of electricity markets, because you effectively get to subtract out the price changes in natural gas markets when studying electricity prices. It's necessary usually because natural gas generators are almost always going to be the marginal generator in energy markets, because they'll be the most flexible to move up and down and will typically get cleared as ramping generators. So the sort of process that they do is they bid to recover their costs, which are going to be capital costs, downtime, times when they aren't cleared in the market. They want to like bid high enough that they can recover all of those costs. The market operators monitor gas prices and what gas generators bid, and if they start bidding out of line with what they typically do, that's when they come in with market mitigation measures that, hey, this generator is trying to manipulate market prices, and they get fined accordingly. Wind turbines, a little bit different because they don't have fuel costs, but they do get a wind production tax credit. So as long as the price is above negative $26, they make money. So generally they will offer in at whatever they forecast with a bid price of negative $26. Again, they get paid whatever the clearing price is rather than what their bid cost is. So this makes sure that they get cleared at their price. And, maybe they have to do some hedging so that they don't have to buy back their position too much if there's wind forecast errors. But this is more or less what a wind turbine would be doing. It's similar with solar as well. Hydropower is an interesting type of generator because of how far into the future they have to forecast how much rain is going to be falling and filling up the reservoir, right? So there's similar fuel costs, $0, but they have requirements on minimum, maximum water levels within a reservoir. They have to predict, when is seasonally water going to start filling up the reservoir, how much is it going to fall, how much can we sell now, and you get into this opportunity cost of how much should we release now versus how much should we save and release in the future. Also, we have regulatory constraints on water levels. How does that all affect each other? And a really interesting one is that you release water from one dam, it flows downhill to the next dam, which starts to fill up and now has to sell off its water as electricity to be able to maintain water levels. You'll have dozens of these dams in the same river that all flow into each other. And it's a big optimization problem of like how much water should be released from all dams for an entire season based on waterfall estimates. So there's this interesting thing of combining this long-term uncertainty around weather and then this very short, fast-changing electricity markets, typically solved with stochastic dual dynamic programming. This is, I think, a good example of like combining like very long-term and very short-term dynamics for a generator as how it will be bidding within markets. Battery storage is also an interesting one. Generally, it's pretty straightforward. It's buy high, sell low, buy low, sell high. They just have to make sure the price difference is enough to cover the efficiency as well as degradation of the battery. It will only have so many cycles available before it loses too much of its capacity. I haven't mentioned this for other components, but it's worth maybe knowing for battery storage that they are typically have a lifetime of about 20 to 25 years, and that's estimated at 1 charge cycle per day. And then you have a lifetime of 25 years for the battery. They can be standalone. More commonly today, it's being coupled with renewable energy so that you can stabilize the output of a solar farm or a wind farm so you can better predict how you should be selling your electricity. And an example of a standalone battery, if you have a 100 megawatt, 400 megawatt hour battery, it takes 4 hours to charge, 4 hours to discharge. Basically what you would try to do is predict the 4 lowest cost hours of the day and self-schedule to charge those hours, and the highest cost hours of the day and schedule to sell at those hours. And then you can arbitrage the price difference throughout the day. And this is actually something that does help out a lot with ramping because low prices generally mean that use up all that extra renewable energy, and high prices mean there's ramp constrained, there's these really expensive natural gas generators running because they can ramp up quickly, but you can discharge your battery instead to capture some of that value. These things can also be really big. If you've seen that picture there, that's a 390 megawatt solar farm and 140 megawatt 4-hour duration battery in front of that. But it goes way off into the distance, and on both sides it keeps going. So these can be really, really big facilities.
Today, say I'm a big bank, and I can invest in a battery farm and then play around with the battery. Am I allowed to do that?
Yeah, so the question was about being able to just be some outside investor that wants to go build a battery and then trade energy prices. Yeah, absolutely they can do that. You can also do that without owning any assets too, virtual trading, but you can do it with batteries as well, and that's been maybe not the most common players in doing that, but that's what a lot of people are doing. So the company that I worked at this past summer, I think they've built about 5 gigawatt hours of battery storage this year. A lot, right? And all of it is in Texas and California, and it's all just trying to capture these price spikes. It's having good forecasts of energy prices and being able to then schedule a battery to charge in those time periods. But they're 25-year assets, so you want to put it somewhere where you think there's going to be good price differences well into the future. And that's one of the bigger challenges is like, there's big price differences now. If everybody builds a battery here, there's not going to be any price differences anymore. Right? The more that gets built, it captures all that value out of the system. Yeah. So the other side of the equation of these load-serving entities, they're the ones that are buying electricity, right? So they buy wholesale electricity, they sell it to retail customers. They are different kinds of long-term contracts that they will also be involved in that then like mitigates some of their price exposures, but then they also will be bought then in day-ahead markets, and the real-time market effectively settles their forecasted load with what the actual load was. In day-ahead markets, they also won't buy all their electricity. They'll buy maybe 90% of it. You can kind of see that in the figure here. So the cleared demand in the light green is what was cleared in the day-ahead market, whereas the dark green is the forecasted load. So what was cleared is not all of the forecasted load. There's a bit of a gap there. And yellow is the actual demand in real time that happened on this day. So that was mostly higher than that forecasted load, but now that difference between day-ahead cleared, real-time load is what's going to be transacted in the real-time market.
So the
Yeah.
demand is given, so when demand is placed, how small is the interval for demand?
Every 5 minutes, is that where?
The day ahead, so I give demand for every 5 minutes.
So the day-ahead market is 1 hour resolution, and the real-time market is 5 minutes. So yeah, that's also some aspect of like the price differences is course of resolution in real time on when those time intervals are occurring. So this last slide is about industrial users, and it's a bit wishy-washy. It's not that specific or technical because sometimes this can be fairly hard information to find. There's some levels, it's like if you're directly connected to a transmission grid, you would be able to fully participate in markets, but if you're connected through a utility, you're kind of limited by what the utility lets you do. And generally, I think a utility would be pretty incentivized to make some agreements of like, hey, we will let you just buy wholesale rates and then you adjust your power accordingly. And that can save the utility from a lot of price exposure, right? But it all kind of comes through of like, what are the different types of contracts you can get with the utility and how you buy your electricity and some of that variation. A lot of these custom contracts can exist. So for example, I know Madison Gas and Electric has a specific electric contract for athletic field lighting. Like the reason for that is that it's a very specific amount of electricity usage for a set number of hours in a day. And if they know that this field is going to be lit from 5 p.m. to 9 p.m. every day in the fall, and it's going to use 10 or maybe called 100 kilowatts or 50 kilowatts at a time, they can just plan that out into their forecast of how much electricity to buy. So like having that very specific amount is useful for MG&E to buy electricity with good forecasts about it. So all of these things can be open to very specific contract negotiations, but it's not super clear because it's all this individual work between industrial users and utilities and how that works. But like data centers are examples of types of utilities or companies that would be using these kind of agreements with utilities, and other really large industrial energy users can be as well. But yeah, you could participate either through like demand response, where you change your output, reduce your output if prices go high, or directly energy trading if you can actually participate in day-ahead and real-time markets to buy electricity for your industrial facility. Any questions? Let's look at a very basic example of an energy demand, we'll call it an electrochemical cell here, and participating in an energy market. And so the basic idea I'm going to model here is we have some load. It can use up to 100 megawatts of electricity. It is producing, this electrochemical cell, some product that's worth $40 for every megawatt of input you put into the cell. It has these ramping limits, maybe 60 megawatts an hour without degradation. I have no idea if that's a real number. I made that up. But the prices here, so this blue line on the curve here is real. This is the ERCOT North Hub real time on, I believe this is August 1st of 2023. So given the price of electricity you might be buying, the price of the product you're producing, when should you run this electrochemical cell? When should you turn it off? Mostly it's kind of straightforward of like, well, when the price of your input is higher than the price of your output, you should turn it off, right? This is what you would want to do ideally. But if you're ramp limited, it might actually look something more like this. You have to like ramp down below the actual expected price increase so you can not buy that super expensive electricity and try and ramp up and go around within that little envelope that you have access to. And I had this little basic optimization problem to do that of like, oh, optimize the output given the perfect knowledge of the price forecast. That's a super basic model, and there's tons of additional considerations that you'd have to do about this. On the operational side, there's the cost of actual chemical storage and transportation and how you would actually be selling it. Maybe you have price forecast instead of the perfect knowledge example that I have here is like you can forecast maybe the price will go up, but do you know how high and how do you hedge against that? Or you can do stochastic optimization. You might be bidding some of that amount in ancillary services markets, whereas like you're planning to run and then suddenly you have to turn down your generator, or sorry, your electrochemical cell usage in response to that. But if you're already trying to ramp down in terms of the energy usage at the same time, maybe you have your ramp can't actually go down as fast as what you're supposed to be doing now. So there can be all kind of conflicts around that. You can combine day ahead and real time. This was just real time prices. One thing that people have also talked about is like marginal emissions or average emissions of the generation that you're using at different points in time. And those are slightly different topics, sort of like how do you want to assign the blame of emissions as the person who consumes 1 extra megawatt right now, or do you consider the average emissions of the grid as, how do you actually want to be assigned the emissions usage of your facility? So marginal emissions will be, if a natural gas power plant is providing the marginal energy right now, that's the amount of emissions that you have from your additional megawatt. If it's average, what if you have a lot of renewable energy and a couple of natural gas power plants are the marginal units? Well, the average emissions are low. Assigning that blame, there isn't specific justifications for those two, but beyond trying to pretend that you're cleaner than you are sometimes. But they're both valid arguments for both. Different types of investment planning considerations around this would be like, okay, you can look at some of these prices, historical or future forecasted prices. How much capacity of electrical chemical cells should you build to consume electricity? Should you be building attached wind and solar, and how much of those to be able to like make sure you run your facility more often using some wind power you built yourself, but also being able to buy some stuff from the grid? What if you oversize that wind so you can run your chemical plants 100% of the time and sell the excess to the power grid? There's all kinds of combinations you can have there. You can have batteries on there that increase the flexibility of your electrochemical cell. The prices went high really fast, but you can't ramp down your electrical chemical cells very quickly, so you power them from the batteries as they're ramping down, and you immediately stop buying power from the power grid. How big should that battery be for what you want to do? All of these are going to be sort of important questions around modeling. How would this equipment participate in electricity markets if you're going to be buying and trading real-time and day-ahead electricity? And of course, the final thing, actual models of electrical chemical cells that are more detailed than what I did with just a ramp rate. But that's for a lot of people in the room here, and what you're actually doing research on is what would those models look like. And one specific thing I might mention about that is that bids are required to be convex for electricity markets. So if you do bids, they have to be a convex bid. So that's the end of this little modeling bit. The rest of this we're going to talk about is some grid data and some context of what pricing and seasonality looks like. Any last questions on the last section? All right. We're also going to take a look at Texas here and what some of their energy looks like. They have the most volatile prices, and they also have a lot of renewable energy that really drives a lot of that, along with the market design, which is not fairly regulated, so they avoid things that require it to run more reliably. So first we're going to just show you here, what does seasonal load look like? We have the load and the net load here, which again is subtract off electricity. So the load in Texas peaks in the summer months, right? It'll be around 70 gigawatts in the summer. This is daily average electricity for each day of the year, 2023. The other 3 seasons are, all pretty similar to each other with around 40, 45 gigawatts of electricity usage. But if we take a look at the net load, it's going to spike up and down a lot more. We're subtracting off renewable energy in this case here, right? And so what that means is that it can change a ton because of all the wind power that's in Texas. Each day can change by 20 gigawatts of wind power. And the rest of the grid has to somehow handle that capacity. So there are 5 load hub locations, and we can look at the prices for these different hub regions and how they are affected by the congestion and the amount of renewables that are going to be on the power grid here. So we're going to take a look at 1 week at a time on 4 different seasons. Here is the first week of January 2023. Sort of the average price on here is about $20, but you have these big spikes. The spike is 5 p.m. or 6 p.m. every single day, and the trough is always at about 2 a.m. every single day. This is the cycle of prices that happens every single day in Texas in the winter. At the higher prices, all those different lines for the different regions, they overlap because they're basically the same price. There won't be congestion. In the little troughs in the prices there, you start to see a little bit of separation in prices between the regions, and that's the congestion between those regions. It's going to be around $5 difference in this week at that. Those price minimums will range about 5 differences between them, and that's a little bit of congestion between these different regions. The spring is a little crazy. We almost have 4 straight days of negative prices in the panhandle of Texas here, and also a lot of negative pricing in West Texas on the green line. The reason for this is that demand is fairly low, but there's a lot of wind in Texas in the spring. All that wind is now causing congestion on those power lines, and it's not selling for very much in West Texas, and they can't move it all to Houston where they're actually using a lot more electricity at that time. So you can get a price spread within Texas about $40, day after day after day when this is happening. We'll still have some crazy price spikes at 6 p.m. every day. In this case, up to $120 on the 5th there. I think that's about it for the spring. The summer is when they use a lot of electricity in Texas again, right? So now we have typical daily prices will peak in the hundreds of dollars, $280 on the highest day here. And because there's so much electricity usage, there really won't be as much congestion because wherever renewable energy is being generated, it's being used, right? Everybody's running their AC. It's hot in Texas in July. So small price spreads, but overall prices are just very high. There aren't really crazy spikes in the middle of the day, again, because whatever gets generated from solar and wind is not going to affect prices too much because whatever gets generated gets used. Prices are high. The West is, in the fall, it looks a lot like the spring, but a bit less extreme here. So this is week of October. Again, similar price spikes, 6 p.m., highest spikes around $95. In sort of the lulls at night when not much energy is being used, it's also going to have the bigger price spreads here of a $25 price spread between Panhandle, West Texas versus the South, North, and Houston areas. So they get this sort of seasonality of prices, right? So each figure here is not scaled to the same level here, right? We have up to almost $300 in July, and the other ones are maybe $100 on the peak prices there. But you have these different trends of congestion, especially across seasons, but also energy usage will affect the energy price across seasons, where the summer is hot, a lot of air conditioning, a lot of energy usage, high prices, not much congestion. Other times of the year with lower energy usage will result in more congestion because all that wind energy being generated can't be used. Along with the fact that there is the most wind in the spring and fall already, even though that's lower energy usage times. So curtailment, people have asked about that already, but curtailment is renewable energy that is unused for one of two reasons. It's either there's insufficient transmission to move that energy to where it's being used, so that's congestion, or there's insufficient dispatchable generation to maintain reliability. So this will be ramp limitations of the available generation on the power grid. And in Texas, this is what that curtailment looks like. So the squares here are going to be wind, and the circles are going to be solar curtailment. Yellow is 100%, and then purple is 10% curtailment of these facilities. And that's primarily all happening in West Texas here. This is, by the way, April 18th, 2023. So you have all this curtailment that's happening in West and a bit of North Texas because there just isn't enough energy usage on this day to have that extra demand to be able to use it in these regions, and there's enough transmission capacity to send it all the way to Houston. Some interesting little things about curtailment is you see a lot of them will go immediately to 100% curtailment, and that's typically because they have this flat price offer curve. For solar, that'll be like $0 a megawatt hour. If it goes below that, they generate nothing. If it's above that, they generate 100%. They have no slope on their price offer curve, so they'll get 100% curtailed if they do get curtailed. The reason for this $0, by the way, is because solar typically uses the investment tax credit rather than production tax credit, which is what wind uses. Is what was available for a long time. In the IRA Investment Reduction Act, changed it so that both technologies can apply for either one of the production or investment tax credits. So that might be changing in the future, but that's the historical reason for sort of why it's primarily solar that gets curtailed first. Question, yeah.
So if they get curtailed, how do they make profit?
They make no money in that period of the day because there's nobody to buy their electricity. So they offered to sell it, right, but nobody bought it because the grid could not take that electricity.
I know that there's still lots of solar waiting to get interconnect to the ERCOT grid.
Yeah.
But if they know the curtailment is so bad.
So this is one day of the year, right? And it's the lowest energy demand day of the year, more or less, where not much energy is being used. So yeah, on that day, it's going to be really bad. In the summer, they can still make a lot of money selling really high prices and a lot of available solar to sell at that point in time. So part of it is that actually building solar is so cheap that even just running in the summer, they can make a ton of money, but they run most of the year, but there are times of the year when that renewable energy just cannot be used and it will not be produced. And then they cannot sell that electricity for that, few hours on this one day. I have a slide here. This is the total amount of curtailment in all the different ISOs to give a sense of scale of where it's all happening. So in ERCOT, it's 7.6 gigawatt hours per year, while the average energy usage, I want to say, is like 40 gigawatts times 8760 hours in a year, right? So a lot more energy is produced than is going to be curtailed, but it's a significant amount within this. And these top ones are really the ones that have built the most renewable energy, and that's why they have the most curtailment. So there's CAISO, followed by where we are in Mid-Continent Independent System Operator, then ERCOT, and then the Southwest Power Pool. And that 10.1 gigawatt hours is largely due to they have a lot of wind. Most days it's like 50 to 60% wind power in sort of the Great Plains area is where Southwest Power Pool is. But they also have a lot of self-scheduled generation that is going to lead to some of this curtailment. They could also build more transmission to move that to other places, but all their neighbors also do a lot of curtailment. So it's been sort of a challenge of like how far away are you going to build some transmission lines. The figure here is about future planned wind, solar, and transmission projects from some of the biggest companies that are doing this right now in the United States. The circles are the solar power, and like you said, there's a lot of that trying to be built in Texas right now. Several gigawatts, I believe, maybe 15 gigawatts of solar being proposed. But they think that they can sell enough of that electricity that it will still be worth it, right? Some of these are also like big long distance transmission lines to try and move this energy from especially where it's being curtailed to where it could be used. An example of this is all these transmission lines running to California from places that have a lot of wind curtailment, whereas California has a lot of solar curtailment. And those two production sources can kind of complement each other in terms of what times of day do they usually peak their production and when is it going to be used. That solar curtailment can maybe head towards the Great Plains, and then the wind curtailment, that all the energies actually can be used in California because of the time of day differences and when those typically occur. One interesting note here is all the tan-colored circles on there is the company I used to work at this summer. They're building a lot of stuff. It's 150 gigawatts of what they have up there. Offshore wind is an interesting one as well. I think the first offshore wind power plant opened in the US this year, but there's also this like giant, I'll say like 5 gigawatt offshore wind power plant being proposed. Right now, I forget if they closed on funding last month or not. I don't remember the news, but stuff is still happening, that's for sure. Oh yeah, 10.1 gigawatt hours is about 200,000 kilos of hydrogen if you want a chemical amount for that. Is that a lot of hydrogen? I think it's a lot of electricity, but. Yeah, marginal emissions, average emissions again. This is something worth talking about in the realm of curtailment especially, because like what does curtailment mean for marginal emissions and average emissions? And it's like if you use more electricity, are you using that curtailed energy or not? It depends on where you are on the grid. If you're in a part of the grid where that energy is being curtailed, if you use another megawatt of power, you're using that 100% renewable energy in whatever facility you're running. But if you're in a different region than that curtailment, you're across the other side of this congested transmission line, you're probably going to be using a lot of natural gas power as your marginal emissions for that. So prices can indicate, curtailment by all this like very low or negative pricing, but always buying low prices doesn't always mean that you're using up curtailed energy. It's not 100% clean. So they're related, but not exactly the same. And it's worth knowing about if your goal is to like, use up all this curtailed energy, you kind of have to model the grid side of that to know if you're using more energy, is it the curtailed stuff or is it something else? Two more slides. It's worth knowing where are all the generators in the United States. These are all the generators in the United States, colored by the type of generation and the size is the megawatts of it here. And you can really see how much wind there is in West Texas, right? There's a lot of green dots there. And all that wind goes up through the sort of central Great Plains, which is Southwest Power Pool region, a lot also in Iowa, a lot of wind power there. It's interesting to see some of the delineations around state borders, which states have some solar incentives and which don't. You can really see southern Minnesota there, right next to Wisconsin. They have a lot more solar than we do, distributed out through a lot of the rural area there because they have a lot more state-level solar incentives for doing so. And there's a good amount of history you can also see within here. So there's a string of coal power plants in the dark brown here, which is along the Ohio River, which is powering the former Rust Belt. All the coal power plants built using the river as cooling for them, and it was all powering heavy industrialization in the United States 80 years ago. Also, we have a ton of hydropower in the Pacific Northwest on the Columbia River. This one hydro plant here, I believe, is 18 gigawatts. It's the largest generator in the US. And a big reason why Boeing is in Washington is because aluminum processing is there because it's so electricity intensive, and hydropower is very cheap, very available electricity. So there's still a lot of history behind that. Locations of industry is really energy availability in the United States. And to note maybe is also how sparse the West is outside of California. There's not a lot of generators there. The generators that do exist are just built along transmission lines to move it to other places. So you have these lines that run from Utah towards Las Vegas here, and then another transmission line that runs up to a bunch of industry that's sort of in eastern Washington state, I believe there. So some interesting history that runs behind where generation is. Similarly, there's where are all the transmission lines? I got this data from the Energy Information Agency, and the voltage and the color are both indicated. Sorry, the size and the color indicated by voltage. So higher voltage lines are in the white, larger lines, and you see how much of this in sort of, I believe this is sort of eastern Montana, I think. All these power lines running east from there into the rest of the upper Midwest, providing a lot of electricity. The biggest power line in the country here runs from the Columbia River to LA, and it's, I want to say like 4 gigawatt power line. Provides a lot of electricity from very cheap hydropower along the Columbia River hydro dams down to LA, which has some of the highest electricity local marginal prices in the country. So a lot of infrastructure. You see how empty Maine is here? But the Florida Keys have their own power line. Some interesting differences across. That's going to be about everything that I have to share. So you can ask some more questions as we wrap up here. But the goal of this is why does the power grid exist? It moves electricity around, and having large interconnect systems averages out variations. This is, in the past, it was like getting better generator uptime, but today it's also about better using all the renewable energy by having large connected transmission grid to move the energy around as it's produced to where it's needed. Markets and market clearing are used to determine when generators should operate and how much, and it's an optimization problem to find the lowest cost production possible, with some additional reliability services from ancillary services to provide safe operating points and the ability to ramp up and ramp down as energy demands change and forecast errors occur. All the participants are here to buy by buying and selling electricity. It's every day, it's every 5 minutes, and it's a very fast process that can have very fast price changes in electricity. And the constraints in the power grid are what creating these price differences, and its inability for transmission to move that around. And like we saw in ERCOT, just picking out a random week in the spring, you get $40 price difference in the day-ahead market prices there. The flexible loads are a good way to be able to unlock some of that value. By being flexible, you can capture some market value by ramping up and down as prices change. The big question is, are your capital costs too high to allow a low capacity factor of some equipment that's going to be always ramping up and down and trying to capture price changes instead? So that's everything that I have. I will take any more questions. We have the room reserved for another hour still. So we have some time, but thanks for coming. Yeah.
There's a lot of curtailment in solar because of those flat offer prices. Is there an incentive to do that, or to?
Yeah, so the reason for flat offer prices in solar, and wind will have also a flat price, it's just minus $26 instead. The reason for that is because if the price is over $0, they make money. If it's below $0, they lose money. So no matter what amount of electricity they produce, they have no marginal cost, so they will just offer a fixed amount. If they ramped it a little bit, that means they wouldn't produce as much power if the prices was around $1 and their maximum output offer price was $2. They would not generate power in that case, but they would have to generate power at negative prices, but have to pay into the market for the market to take their electricity. So the reason for flatness is because they have zero marginal cost. And they really don't have any incentive to do something else because they lose money if they do something else. So for that reason, if the price is jumping up and down between negative and positive prices and their marginal price is zero, they're just going to curtail or not curtail depending on how it clears. But they don't have a reason to do anything else. Yeah. A reason for them to have a battery is to charge up when prices are negative, charge the battery from their solar panels, and then sell that later in the day when prices are higher. Yeah. Another question in the back?
So you mentioned solar are more likely to get refinance
Yeah.
than wind because they have a different.
Yeah, so traditionally there have been different tax incentives for wind and solar, where for solar it's the solar investment tax credit, where they get a tax credit on the amount of money they invest on building the infrastructure, like the actual solar plant. And for wind power, they get a tax credit for the amount of energy that they produce. That's the wind production tax credit. And as a result, the marginal price of wind is lower because they get paid $26 for every megawatt that they produce, whereas solar gets paid zero, but they got a tax credit in building the facility in the first place. Yeah.
So is it the curtailment purely due
Yeah, yeah. It is always going to be because the power grid is constrained in some way, right? So the transmission grid isn't able to move more electricity between two places because it's at capacity, is an example of one of those constraints. It can also be the ramping constraint, that they need to have a power plant available that can be dispatched to produce more power later in the day. That's probably going to be like a natural gas power plant. But that power plant will have a minimum power output. So they need it to run. And to make that happen, maybe they have to curtail some wind and solar as well, because you can't have production exceeding demand either, right? So that would be an example of like a ramping constraint for later in the day that would cause curtailment now. Most generally, it is the transmission line constraints that are going to be causing the curtailment. But as even more renewable energy is going to be produced, some of that ramping will also be an issue that will cause more curtailment as well. Yeah?
I have a question in the optimization problem.
Mm-hmm.
So they are minimizing, the ISO is minimizing the overall cost for CGMP, like where is CG is the bidding cost?
Yes, it is the cost of producing electricity is what they're minimizing, right? So you need to buy electricity, you need to buy up to whatever the utilities are buying, and you need to figure out what's the minimum cost of producing that, so what's the lowest cost generators that are going to be participating in that. You know, it's renewables that bid about $0, it's going to be hydro that's going to bid like $10, and nuclear bidding $10, and then natural gas is going to bid $40, and maybe that gets cleared or maybe it doesn't, depending on if it's needed, right? So it's choosing which generators to use to produce electricity, choosing the cheapest ones, given constraints on the power grid of where the power can flow.
That's not good for the supply.
Sorry, what?
That's not good for, so if suppliers want to formulate optimization problem, they would formulate like maximize the profit for them.
Yes. So yeah, you're saying that what suppliers want to do is they want to maximize their profit by, selling everything for more expensive. But that would be manipulating the market with their market power. And so yeah, they wouldn't do that. The design of the market and this clearing price is to incentivize honest bidding of marginal cost by all the generators. So that if you bid more than your marginal cost, you just won't get cleared in the market. So you actually make even less money than no money. Yeah, it's not for the incentive of the generators, it's for the maximizing the market surplus. Is that right? Yeah. Well, if there aren't any more questions, we can wrap it up. You can always send me an email if you have any more questions. I'm happy to talk about it. And can call it a day.